Okay, let's start with a question again. What's the kinetic energy of 3 kilogram mass moving around a circle of radius 0.8 meters at 5 radians per second? Pause, solve the problem. I'm going to continue. Okay, well, what's the kinetic energy? The kinetic energy, of course, is 1/2 mv squared, but we're not given v, we're given the angular velocity. Of course, we're given the radius of the circle, so we can find the speed, the v, of the mass. Okay, so speed of the mass, as we just saw, is equal to the radius times omega. Again, if we multiply the 5 radians by the radius, we get the distance. Okay, 5 radians times 0.8 meters is 4 meters. So the 5 radians we move in a second, in angular terms, is equivalent to the 5 radians times 8 meters, or 4 meters per second. So that equals 0.8 meters times 5 radians per second equals 4 meters per second. So the kinetic energy is 1/2 times 3 kilograms times 4 meters per second, quantity squared, equals 16,824 kilogram meters squared per second squared, equals 24 joules. Now, in symbols, we think of a mass m moving with angular velocity omega on a circle of radius r. What is its kinetic energy? Symbolically. Work that out. Okay, you should have gotten the expression for kinetic energy rather easily. Kinetic energy is 1/2 mv squared, as we saw, and v is r omega, as we have seen. So that 1/2 mv squared is 1/2 m times the square of r omega. Again, you should think back and think through what these things mean. But when we square that, we get this expression. So this is the expression for the kinetic energy in terms of the mass, the radius, and the angular velocity. Now, this actually gets us someplace. Okay, we have the definition of kinetic energy in terms of mass and velocity. And now we have the expression for kinetic energy in terms of mass, radius, and angular velocity. The velocity, as we know, is analogous to the angular velocity. The angular velocity and velocity are analogous quantities when you think about the comparison between linear motion and angular motion. These formulas are kind of similar. Here we have a mass. So what is it in this formula that would be analogous to the mass? Think about that for a second. Form an opinion, and then consider the answer. I'm going to say that, well, the mr squared. The 1/2 is the same. This is analogous to this. So this has to be analogous to whatever else there is in the equation, because this is the only other thing in this expression, that equation. Okay? So mr squared is going to be a quantity that in some sense is analogous to mass, at least when calculating kinetic energy. And as we'll see, the analogy goes much further than just the calculation of kinetic energy. So we call this mr squared the moment of inertia. Now, moment can be thought of as a rotational influence that works within the context of rotational motion. So the moment of inertia, well, inertia, mass is inertia against acceleration in any direction. Mr squared is what you think of as resisting the influence of a torque or a moment. Okay, we'll develop that idea a little more later, but that's the reason for the for the name, or that's some indication maybe of the reason. I'm not sure historically exactly how that came about, but that makes, I think, a whole lot of sense. So we define well, let's see. It symbolizes I. So I equals mr squared. Now, if we have, let's say, the 3 kilogram mass, and in addition, we have 2 kilogram mass. On a circle of radius 0.4 centimeters. So let's say radius 1.3 meters. And I'm getting ahead of myself. We'll say, what is its kinetic energy? Should have put the 5 radians per second in earlier, but I'll just add it here. At 5 radians per second. Okay? You should work that out. Now, I'm not going to give you time in the video to work it out, but it's fairly easy. The velocity is 1.3 meters times 5 radians per second, which equals 6.5 meters per second. Its kinetic energy is 1/2 mv squared, 1/2 times 2 kilograms times 6.5 meters per second, and squared. And if we square 6.5 meters per second, we get about 42 meters squared per second squared. So that's approximately 42 joules. Significantly more than the more massive 3 kilograms moving in a circle of radius only 0.8 centimeters. Since that radius is proportional to the, well, since we have the 5 radians per second on both circles, the 0.8 meters is going to correspond to 0.8 meters of radius, excuse me, will correspond to 4 meters, say that correctly, a 0.8 meter radius and a 5 radian angle is going to give us 0.4 meters. So we have 0.4 meters, 4 meters per second. Here we have 1.3 meters times the same 5 radians per second, giving us 6.5 meters per second, and that velocity is going to be squared. So squaring 4 meters per second, squaring 6.5 meters per second, even though we have a lesser mass, the square of this exceeds the square of this by quite a bit, so that we get almost a doubling of the kinetic energy. Okay, we now ask for this second object, what does I omega squared equal? What do we get if we calculate I omega squared for the 2 kilogram mass moving at 5 radians per second on a 1.3 meter circle. So you should figure that out before I proceed to calculate it, but here we go. Okay, well, of course I got to spread this over the bottom of the board here, but the moment of inertia is mr squared, which is 2 kilograms, times 1.3 meters quantity squared. And 1.3 squared is 1.69. You double that, you get 3.38. You can check my arithmetic. Kilogram meters squared. Now, if the moment of inertia is 3.38 kilogram meters squared, then I omega squared would be that multiplied by the 5 radians per second quantity squared. Well, 1/2 of that multiplied by the 5 radians per second squared, 1/2 I omega squared. And, gee, I don't think I ever mentioned 1/2 I omega squared. So, could be that I asked you to do something that, okay, well, I did ask you to calculate I omega squared. You knew how to calculate I, so hopefully you were able to get that much. And I didn't put the 1/2 in the I omega squared either. So I made a couple of mistakes here, for which I apologize. Just to explain this, this is 1/2 mr squared omega squared. If I equals 1 mr squared, this is 1/2 I omega squared. So the kinetic energy is 1/2 I omega squared. And if you calculate I and then do the calculation 1/2 I omega squared, you should verify that with this moment of inertia and this angular velocity, you do get approximately the 42 joule kinetic energy.